This isn't to be confused with intramolecular forces. And in your books, you should be reading these pages here on polarity. So that's in your theory workbook here. You should be going over page 24, 25, 26. You should be going through 27 and 28. So we'll be talking about those pages, and also 29 and 30. Okay. So before I go over intermolecular forces, I need to talk a little bit about intramolecular forces so you don't get confused between the two. But today's lesson and what you'll be tested on is the intramolecular forces, and there are 3 of these. Okay, so as a side note, intramolecular is within the molecule. So bonding forces holding the atoms of a molecule together. So if we've got oxygen bonded to a hydrogen, the intramolecular forces is within the molecule, so it's between the oxygen and the hydrogen. Today, I'm going to talk about an intermolecular force. If you have an interschool, do you know what an interschool is? In the South Island, we call them interschools. What's an interschool? Between 2 different schools. So if we were playing rugby, it would be between Rangitoto College and Westlake. So intermolecular forces is the force that occurs between molecules, okay, between 2 different molecules. So if we have water, I've got a water molecule here. This is my water molecule. And here is another water molecule here, okay? And it's between the 2 different molecules. This is the intermolecular force, okay? And this is responsible for phase changes. When we heat a molecule up, we're breaking away the intermolecular force. So it's not the intra, it's not between. The molecule is still the molecule. We're just breaking away further apart and further apart. So we've got a solid, then we've got the liquid, and then we've got the gas phase when we're putting them further apart, okay? Here, the 3 different types of intermolecular forces that you need to know about. The first one is temporary dipole, okay? I'll go into what dipole means. Temporary dipole is the weakest, and it's in all types of molecules. So there's polar and non-polar. Permanent dipole, I try to think of this as the P and the P. Permanent dipole is only in polar molecules, and there's hydrogen bonding. This is the strongest of all the type of intermolecular forces. All right. Okay. So I'm going to first of all talk about temporary dipole forces. So temporary dipole forces occur between non-polar molecules. Can someone name a non-polar molecule? Name what's the basic one that little kids find funny if they do them, or cows pump out? Methane, CH4, okay? So if we've got something like CH4, we know that it's a non-polar molecule because the dipoles cancel, okay? And if I was to draw a CH4 molecule, you know that we've got the molecule, we've got the positive nucleus and the negative regions of electron repulsion around the outside, okay? So you can see that here, okay? So start off with there's no polarity between the 2 molecules. Can you see that? There's no polarity. So you've just got your CH4 molecules bouncing around. Another molecule that's got no polarity, or other molecules, what are the diatomic molecules? Can anyone name them? What are they? Sorry? How do you remember the Honkelbrief? Okay, so Honkelbrief. Okay, so these molecules are always diatomic. They have to exist only as pairs, all right? So if you've got Br2, all right, if you've got Br2 molecules, bromine molecules, these bromine molecules are always randomly moving about, okay? So if you looked further into the bromine molecule, you'd see that they've got a positive nucleus and negative electrons around the outside. So there's absolutely no polarity. Do you understand what I've drawn there? Okay, but as I said, these molecules are always randomly moving about. And there's going to be, when the molecules come close together, and for a slight moment, there will be a change in the electrons. So delta means slightly negative, and delta positive means slightly positive. So if you've got a Br2 molecule, and a Br2 molecule, all right, in it, for a temporary amount of time, there'll be a change, a slight little bit change. One end will be negative, one end will be positive, and on the other Br2 molecule, one end will be negative and one end will be positive. And what you will have here is a temporary dipole bond, okay, where the Br2s are slightly attracted to each other. So this is a temporary, so it only occurs for a fleeting moment, dipole bond, okay? So there's a slightly positive charge and a slightly negative charge, and these two are attracted. But remember, these molecules are always moving randomly about. So these are short-lived, and they're the weakest type of force. Okay, so temporary dipole forces occur in molecules without dipoles. Okay, so they're only, well, they do have a dipole, but it's only very, very temporary. So, for example, the noble gases, they do not have dipole moments. They're still attracted to each other at low temperature. So noble gases are always moving about, but for a fleeting moment, one end will be negative, one end will be positive, and there will be that temporary dipole force of attraction. Okay, the next type we've got is permanent dipole bonding. Permanent, remember, P goes with what? P goes with polar, okay? So polar molecules, all right? P goes with the polar molecules. So in temporary dipole bonding, molecules with dipole moments attract each other. So the dipoles line up so that the positive and negative ends are close, okay? So if you've got a molecule, okay, you've got a permanent dipole that occurs where the positive and the negative end line up close. And this is just something like if you've got a molecule such as HCl, okay, and here HCl, all right, which one's more electronegative? Okay, electronegative, and you know that there's a slightly positive charge on the hydrogen and a slightly positive charge on the hydrogen. So there is a dipole there that's set up. So the electrons are dragged more towards the chlorine, and here the electrons are dragged more towards more towards the chlorine, and here there's an attraction, and that's a permanent dipole force. Okay. Here I've got my favourite, water. Water, okay, we know that there's an uneven sharing of electrons in here, and we know that the hydrogen is slightly electronegative. Here there's slightly slightly electropositive. Hydrogen is slightly electropositive, and oxygen is slightly electronegative. What's causing the uneven sharing of electrons, please? What's causing it? Why is oxygen hogging more of the electrons? Why? No, nothing to do with valence shell, because remember, we're not talking about ions. We talk about valence electrons and ionic compounds. These are covalent. They're sharing their valence electrons. But what is it about the big oxygen atom as opposed to the little hydrogen atom? What's the big oxygen atom, Grace, got inside it that hydrogen doesn't? It's got what? It's got more protons. So oxygen has got a big positive nucleus, 6 protons. Hydrogen's only got 1. So oxygen is hogging more of the electrons more towards it. So there's an uneven sharing of those electrons, and that occurs in all the water molecules. So you've got slightly positive ends, a negative end, slightly negative end, slightly negative end, slightly positive end, slightly positive here, slightly positive, slightly negative. So between these, you're going to get an attraction, and that attraction is a type of permanent dipole bonding, which accounts for why water has such a high boiling point. Okay, all right. I now want to move on to hydrogen bonding. This is strong, okay, very, very strong. And hydrogen, what's so special about the hydrogen atom if you were to draw it? Remember? What's so special? It's only got 1 proton. So hydrogen's only got 1 proton in its nucleus. It's got no neutrons, and it's got an electron spinning around the outside. Hydrogen is special because it's the smallest atom. If you bond it, hydrogen bonding only occurs between fluorine, oxygen, and nitrogen. My nephew likes to think that chemistry is a lot of fun. Can you see it spells fun? So hydrogen bonding only occurs between the fun elements. That's fluorine, oxygen, and nitrogen. And this here is a type of hydrogen bonding. It's very, very strong. So oxygen and this fluorine in this bond, it has more of the electrons, and hydrogen ends up with a slightly positive charge. So there's a dipole here, and same with oxygen, and here's hydrogen, and here's nitrogen, and here's hydrogen here, okay? So there's an uneven sharing of the electrons. Here, if I look at it, hydrogen bonding has effects on physical properties, and this accounts for water's high boiling point. I'd like you now to, can I get the worksheet that I gave you? I gave you 2 bits of paper, please. Can I have it? Yep, here. Yep, cool. Okay, so for this polarity section, you need to memorise these 2 essays, and you have to be able to, you'll be given a question of either drawing a Lewis dot diagram or being given a Lewis dot diagram. So you need to, in the pictures, identify which atom is slightly electronegative and which one's slightly electropositive. Could you tell me, in the IF bond, which one's slightly electronegative? F, okay? So slightly electronegative, slightly electropositive. So the dipole moves this way, okay? You have to be able to draw these dipole moments in for an excellence. And you've got to be able to remember these statements here, which I've corresponded with examples. So polar bonds result due to the difference in electronegativity between the I and F atoms. In your essay, you need to identify which one's slightly electronegative and which one's slightly electropositive. The molecule is not symmetrical. How do I know it's not symmetrical? Because if I do a mirror through it and fold it this way, okay, straight up and down, it's not going to be symmetrical on each other. So the polar bonds do not cancel. So the IF molecule, 3 molecule, is polar. You have to be able to memorise this essay, so learn it to be awarded the grades here. Okay.